Today we are going to be talking about the beginning of Unit 4. Unit 4 is going to be all about graphing and writing transformations of functions. This will include characteristics. 4a is graphing the absolute value functions. Mine is going to begin on page 33, but remember yours may be on a different page. You are going to get several pages of materials that we are going to cut apart and glue or tape into your notebooks as you see fit. I decided to go with the review material first. So we are going to be talking about some vocabulary. A relation is a set of ordered pairs that made up of inputs and outputs. Remember that inputs are the same things as your x values, and outputs are your y values. So in our ordered pair, we have an x and we have a y that are made up together to create a relation. Remember that absolute value is the distance a point is from 0, and remember that it is always positive. Okay, so when we talk about absolute value today, we're going to remember that anytime we take the absolute value of something, that it's always going to be positive. And because we're going to be talking about transformations, when you talked about transformations in algebra and geometry, you did slides and rotations and reflections. Today we're going to focus more on the sliding component, and we're going to give it some new names, so just be prepared for that. A transformation is a change in shape, size, or location. Okay, so what I mean by shape is it might stretch it or shrink it, the size is going to change, and the location is going to change. So let's take a look at what some of these transformations are. All absolute value functions are transformations of a parent function, y equals the absolute value of x. So I want you to understand that a parent function is basically a function that has not been adjusted in any way, shape, or form. Okay, and we can also write this parent function as f of x. Remember that y and f of x are interchangeable. So what we're going to do is we're going to create a table of values here to graph the function of absolute value of x. So I'm going to create an x and an f of x equals the absolute value of x, and then my output is going to be my y. And I'm just going to show this middle table column just to show you where we do the computation, but it's not always necessary. So if I choose the x value -5, I'm going to take the absolute value of -5, which I know the absolute value of any number is positive, so it's going to turn out to be a +5. So my ordered pair is going to be -5, 5. So on my graph, I come over -5 and I come up 5. And I'm going to repeat that using a few x values. And remember that these aren't the only values that are in the graph. These are just the ones that I'm choosing to compute today. And so for each one of these, we're going to take the absolute value. And remember, whether it's positive or negative, my answer when I take the absolute value will always turn out to be positive, except when it's 0. 0 is never positive or negative. And so we create ordered pairs based off of our location with our x and our y value. So I'm going to plot these, and go ahead and plot them on your paper as well. As you can see, I've filled in my graph, and I want to draw attention to this point right here on my graph, this point is known as the vertex because it is the center point where the graph comes together. And notice that just because I only use these points doesn't mean that these other points that are in here don't exist as well. And you want to make sure that you have arrows on both sides. So the vertex of this function is the location of where the graph meets, where the point of the graph is. And it's always going to be an ordered pair. Okay? And the vertex is basically that meeting point where the graph changes direction. The domain from Algebra 1 is our x value, and the range is our y value. So when we look at this graph here, you can see that my x values are both going positive and negative. But let's remember that we read graphs from left to right. So if I'm reading it from the left, I'm coming in and then I'm going to the right. I'm using every x value. I'm going from negative infinity is less than x is less than positive infinity, or I could say that it's using all real numbers. This is going to be how you're going to see it in Algebra 2, but I'll accept either one of these answers. For my range, we want to remember that that's y. There's nothing down here in the negatives on the y, which means that we're starting at 0, and I can actually be equal to 0 because it's a number. I can't equal infinity or negative infinity because I don't know what those are. Or we could say that y is greater than or equal to 0. Either one of those, again, is acceptable in our class, but when you get to Algebra 2, you're going to need to write it like this. Now we need to talk about what increasing and decreasing is. So I want you to look at this graph and ask yourself, what's happening on the left and what's happening on the right? Notice that I'm having to turn my pen, which means that this has a certain kind of slope and this has a certain kind of slope. Well, we read graphs from left to right, so that means that from the left, my graph is falling, which means that it has a negative slope. And so I'm going to say that my graph is decreasing from negative infinity is less than x is less than, 0. Because at 0 it changes, right? This is my changing point. This is where things start to go in a different direction. And it's a positive slope from 0 to positive infinity. Now, as I mentioned in class, we can't be equal to 0 in two different spots. So we're not going to be equal to 0 at all. It's like a U-turn. When you turn around, you're not going north or south or east or west. So we want to make sure that we don't include those. So let's take a look at what happens when we start to change some things. Okay, this is the basic. This is what the parent function looks like. Now let's see what happens when we start to do some changing. Okay, so I'm going to introduce to you horizontal and vertical transformations. Now remember that horizontal means we're going right to left and vertical means we're going up and down. These are actually considered rigid transformations because they move the same direction on the graph at the same time. And since all the points are moving at the same time, that means that we need to take a look at a different style of equation. So it's still an absolute value equation. It just looks a little different. We've kind of added some letters here. Okay, but these letters are important. The H is describing the horizontal shift. H for horizontal, because of the opposites function, because of the opposite operation, this works the same way that it seems. So horizontally, meaning that when x plus h appears in my equation, I'm actually moving left. And when I have x minus h, I might think that that's moving left, but it's actually moving right. So anytime you see the h represents horizontal, you're going to do the opposite of what it says. The k in the function is our vertical shift, and this works the same way that it seems. So when k is positive, when it's plus a number, we're going up. And when k is minus, so minus k, we're going down. Okay, so remember that h is horizontal, and that's going to be inside the absolute value, and k is your vertical, and that's going to be outside. What we're going to do is we're going to take a look at a couple of examples. I'm going to do a couple with you, and then I'm going to have you finish the rest of them up on your own. As you can see here, I've taken the reminders that were in our notes, and I've just kind of cut them apart and put them at the top of the page so that as I work through this example, I have those reminders. So this particular example already tells me that my graph is moving to the right and moving up because I have a -3 and a +2 for my h. But what I want to do is I want you to recognize that the original graph starts at a vertex that's 0, 0. The domain is all real numbers, and the range is y is greater than or equal to 0. Okay, now I'm going to do the shorthand. Remember that you can also make it -infinity to infinity and 0 to infinity. So let's see how that adjusts over here. So if I start at the origin, my graph says that I want to go right 3, so 1, 2, 3. So I'm going to move to the right 3. And then it says that I want to go up 2. So that new point that's there means that my vertex went to the right 3 and up 2. So my new vertex is +3, 2. But it's not going to change anything in terms of the x value, so they're still going to stay all real numbers. What it did, though, was that it moved my y value from 0 up to 2, because notice there isn't anything down here on the graph. So my range is now y is greater than or equal to 2. So when you have an absolute value function, the domain is never going to change. What's going to change is your range is going to either move up or down. Let's take a look at another example. Okay, this time I didn't give you how it moves. So if we look at our equation, y equals x plus 4 plus 1. This plus 4 tells me that I want to actually go left 4, and then the plus 1 means I want to go up 1. So my original vertex that was at 0 is now going to go left 4, up 1. So my vertex is -4, 1. And so if I look at my 0, 0 point, I'm going left 1, 2, 3, 4, and up 1. So here's my new point. And every point is moving in that direction. So I can pick, say, 3 points on the graph to relocate each time. You need to have a minimum of 3. But just like example 1, my domain doesn't change, but my range went up 1, so it is now greater than or equal to 1. Take a look at example 3 and try it on your own. So in example 3, it's just like example 2. We want to look at the equation so we can see that this moves to the left 2, and this time it goes down 3. So my vertex is going to be -2, -3. So left 2, 1, 2, down 3. And if I look at my other points, they're going to be diagonal from those points that I had, remembering to put your arrows. The domain does not change. but my range this time is going to be greater than or equal to -3. Let's go ahead and let's summarize everything that we've done so far with horizontal and vertical shifts. Okay, so we said earlier that the coordinates of the vertex were 0, 0. So I had you write this in your example. So if you go back, you can see that your vertexes move based upon what the changes are in your equations. So this one went left 4 and up 1, so my vertex is -4, 1. Here I went left 2 and down 3, so my vertex was -2, -3. So let's kind of summarize what that means for the vertex. So notice in the equation here I have an x minus h, and here I have an x plus h. What that tells me is that the vertex here is going to be h, because this is minus, so that means I'm going to the right. So it's going to be h comma k. But where I have a plus sign, it's actually going to be -h comma k. And if k was negative, then these would be negative as well. Okay, so just a reminder that h is for horizontal, and we do the opposite. And k is vertical, and do as is. All right, there are 3 practice problems that I have actually glued onto my page next to this so that they're kind of side by side. What I'd like for you to do is I'd like for you to go ahead and do these practice problems on your own, and we will review them in class. Okay, I'm going to go ahead and continue with our notes. We're going to talk about not just vertical and horizontal transformations, but we're going to look at reflections and scales. So this is going to change the appearance of the graph and not just move it right, left, up, or down. So a vertical reflection changes the equation because now there's a negative sign out in front of the absolute value. So putting a negative sign in front will make a graph reflect across the x-axis. So it's changing the y value, which means that it's flipping it upside down. So you can see the difference between graph A, we'll label this as graph A, and graph B. This is the parent function, and this function has been flipped. Okay, so the translation that occurs is just that it has simply been flipped. And so the difference between these two and example C is that this has not only been flipped, but it's also been moved to the right and up. And so from here, we have a couple of questions we need to ask ourselves. Does this reflection affect the domain? It's just moving it from the top to the bottom. So there is no change at all in the domain. However, the reflection does affect the range because instead of the range being positive like it is up here, notice it is now in the negative. So the y will be less than or equal to 0 instead of greater than or equal to 0 in this case. And so that's going to affect just the look of it flipping up or down. The last thing I want to touch on is what happens if we have a number that's being multiplied outside of our absolute value, a coefficient. So if we have a coefficient, placing a coefficient outside of the absolute value function, say A, it's going to give the graph a vertical scale, which means it's either going to vertically stretch it or vertically compress. And what that means is it's going to make it look either taller, shorter. Some people might say it's going to look skinny, it's going to look fat. I just like to say compression and stretch. So if A is between 0 and 1, okay, so it's like a fraction form, then the graph is going to compress with a factor of A. So we're going to shrink it. okay? So it's like a shrink. If A is bigger, we're going to stretch. Okay, that means we're going to make it longer, okay, taller, with a factor of A. Okay, so what I've done is I've got three graphs I want to show you. If the equation includes other types of transformations, then the same rules that we've already been using will apply, and we'll practice those in some practice problems in just a minute. But let's take a look at what happens with these three graphs. Okay, so here you can see that we have the absolute value of x, 1/2 the absolute value of x, and 2 times the absolute value of x. This A is 1/2, and this A is 2. So this is between 0 and 1, which notice it's taken this graph and it's kind of like shrunk it down. It doesn't stop, right? It still goes on in both directions. It just kind of made it wider. It looks like it's shrunk and it looks like it's wider. Okay, whereas this particular graph, the 2, the A makes it look taller. It's stretched it vertically. So the biggest question that we have after we do this is, does the domain or range change at all depending upon what happens to our graph? And I just want you to notice that A in both of these cases is affecting the slope. Okay, so my slope is up 1 over 2, whereas my slope here is up 2 over 1. So the slope changes. The domain isn't going to change. Doesn't have any change. And I didn't move it right, left, up, or down, and so my range doesn't have a change. No change either. There's no movement, and so therefore the vertex stays the same. So we're going to have lots of example problems in class, but these are your notes for absolute value.